In the last video, we talked about the two essential components of a coordination complex, a transition metal cation and ligands to act as Lewis bases donating electrons to it. In this video, I'm going to talk about two additional components that appear in some coordination complexes. So if the charges of your ligands and your transition metal cation add up to 0, then you generate a neutral coordination complex, and that's probably your entire species. But we saw a large number of examples in which the charges of the ligands and the charges of the transition metal cation did not add up to 0. But you can't buy a bottle of cation and you can't buy a bottle of anion. You can't. Species that exist as solids are neutral. And so if your coordination complex is in fact a complex ion, then you will have to have some sort of counter ion associated with it when it's in the solid form. You may also find that in the solid form, because many of these coordination complexes are prepared in aqueous solution, that there may have been water molecules trapped in the crystal as it grew. And those waters we refer to as waters of hydration, and the complex we refer to as a hydrate. And if you are working with some sort of species that has crystallized as a hydrate, you have to include those water molecules in its molar mass. Otherwise, you're not going to get an accurate molar mass. And so an example of a compound containing all of these components is a beautiful bright green crystal that you're going to get a chance to make in the Chem 2000 lab. There is a transition metal cation with +3 charge. There are ligands. Because our overall coordination complex is a complex ion, it has a net negative charge. There are potassium cations balancing that out to make it neutral. And as it crystallizes, we also trap water molecules in the lattice. And so if we were to take this formula and break it down into the pieces, recognizing that the total charges all have to add up to 0, we can work out what the charges of all the different pieces must be. So we have K3 Fe C2O4 3 dot 3H2O. So those are, of course, going to be our waters of hydration. And they are neutral, so they do not affect the overall charge. Our potassium is going to be our counter ion. And there are 3 of them, and we know that potassium takes on a +1 charge. And so that means we have a total charge of +3. Which means, therefore, that our complex ion, since the whole thing has to be neutral, if we're getting a +3 charge from our cation there, our counter ion, that means our iron complex has to have a -3 charge, so that the +3 from the potassiums and the -3 from the complex ion add up to the overall neutral charge. So that gives us the charge of our complex ion. The charge of our complex ion is -3. What about the charges on the ligands? Well, we follow similar logic. The charge on our iron, the oxidation state, is +3. We were told that up here. Which means that if the overall complex has a charge of -3, then our 3 ligands have to have a total charge of -6. And since there are 3 of them, each of those ligands has to have a charge of -2 in order for the overall species to have a charge of -3. After you make those beautiful green crystals in lab, you are then going to be tasked with analyzing them in various ways to determine how pure the crystals you made were. What fraction of those crystals was actually iron compared to how much should have been? What fraction of those crystals was oxalate, which is what the ligand is called, compared to how much should have been? What fraction is water compared to how much should have been? And to determine how much of those crystals is water, you're simply going to take your beautiful bright green crystals and put them in a hot oven and watch them become much less glossy and pretty as the water evaporates out. So essentially, you are going to do this reaction here. You're going to take K3 Fe C2O43 dot 3H2O, and that's a solid, and you're going to heat it up, and the complex salt isn't going to change. All of those components are going to stay the same, but you're going to evaporate off 3 water molecules for every complex salt unit. I can tell you that the molar mass of the hydrated salt is 491.2463 grams per mole, and that the molar mass of the dehydrated salt is 437.2007 grams per mole. And the only difference between those two is whether or not we counted the 3 water molecules, which we have to in the hydrated salt, but not in the dehydrated one. And so really, this is a stoichiometry question. And so we just need to follow our usual 3-step process of figure out moles of something, use the mole ratio, and then answer the question, so that I don't have to write out those whole molecular formulas as subscripts every single time. I'm just going to call this one here A and this one here B. And so if I want to calculate the number of moles of A, that's easy. I've been told that I have 5 grams of my hydrated salt, which is what I'm calling A. And I just need to divide that by the molar mass. And that will let me know that I have 0.0102 moles of my hydrated salt. How many moles of dehydrated salt should I get? Well, it's a 1-to-1 ratio. So my number of moles of B will be equal to 0.0102 moles of hydrated salt times, I get 1 mole of dehydrated salt for every mole of hydrated salt. And that means that I should produce 0.0102 moles of the dehydrated salt. And then if I want to determine how many grams I should be getting out of the oven, then I take that number of moles and I multiply it by the molar mass of the dehydrated salt. So my mass of dehydrated salt will be equal to 0.0102 moles times 437.2007 grams per mole, which is 4.45 grams. And you will be doing this calculation as part of that lab in Chem 2000. So, in summary, every coordination complex has to have a transition metal cation in the middle. And every coordination complex has to have ligands around it, acting as lone spaces, donating lone pairs to it. Some of them also have a counterion balancing out the charge, making the whole thing neutral to give a complex salt. Some of them have waters of hydration, water molecules